Hello all. In our next tutorial, we are trying to interface the OLED display, this organic LED display with the Zinc PL part. So in the previous example, we have been using the LEDs as our output interface. So LEDs, they of course have their limitations. We are restricted by 8 LEDs. We cannot show any alphanumeric. We can show only numbers from 0 to 255 in binary format. So if we have OLED display, we are in a much better position. You can display all alphanumeric, and you can even have running display, so it is not restricted by the size of OLED display. You can have a running display and you can display any amount of information that you would like. But interfacing OLED is not very straightforward as connecting with LEDs. There are a lot of concepts involved there, and involves pretty much of coding. So we will be doing it part by part. Okay, so the details about OLED, you will have to read the data sheet a little bit, and I will also try to explain in the next video. So today's video, I'll be doing only a part of the entire coding. Okay, so if you go to the Zedboard data sheet, and if you search for OLED, this is the only information available to you. So the board comes with an OLED display. This is a 128 by 32 pixel display. So basically there are 128 pixels this way and 32 pixels this way. That is the size of this display. It is monochrome. That means displays will be only in black and white, pure black and white. Okay, so if pixel value is high, means it will be white. If the pixel value is 0, means that will be black. And they are also providing the pin connection information. So these are the pins coming from the display, which are already connected with the chip, the same way LEDs are connected. But this is not one or two wires, there are many of them. And you will see for some pins, the zinc pin, the corresponding pin on FPGA is not given. So NC stands for not connected. That means this pin from OLED is not connected to zinc. Instead, it is directly handled on the PCB. For example, this is the VCC. It is not connected to FPGA, but it is directly connected to the VCC power supply on the PCB. So there is no control for FPGA as far as this VCC is concerned. But for VDD, you can have control from FPGA. So how to use this, we will see later. Today, the only thing I am focusing is this part. So how zinc will communicate with OLED. Okay, so you have to display characters, you have to display number, maybe you can have to display pictures. How this information is communicated between the chip, zinc chip and OLED, it happens through this information, this interface. Now these are two wires actually coming from zinc to OLED, and from the naming it appears like this follows I2C standard. Okay, so please refer to your lecture slides to know more about I2C, inter-integrated circuit communication protocol, which uses serial clock and serial data, only two-wire communication. But the one actually used between zinc and OLED is not I2C. Instead, it is a SPI protocol, serial peripheral interface. Again, you should refer your lecture slides to know more about SPI. The only thing I would like to add is usually SPI is also called a 4-wire communication protocol because there are 4 wires, 1 wire for clock, 1 wire for data from master to slave, which is called the MOSI, master out slave in, 1 wire from slave to master, which is called MISO, master in slave out, and 1 wire called slave select, which is basically used for selecting a particular slave. Now here you can see only 3 wires. So this is the clock signal. This SD in is same as MOSI, master out slave in, and this is the wire through which FPGA will be sending data to OLED. There is no master in slave out wire available. The Zinc chip, it will never read data from an output display. So that's why that wire is missing. Now this CS and this hash stands for this is an active low signal. That means the signal should be low for activating it. Now this signal is same as slave select. So in traditional SPI, this signal is used by the master to choose a particular slave. Now on Zedboard, you can see this is not actually connected to zinc. Instead, it is directly connected to ground on the PCB. So that basically means the OLED is always selected. It's always enabled as far as SPI protocol is concerned. So the only two signals that you can control from zinc for communication are serial clock and serial data, SCLK and SDN. So keep it in mind. Now, no further details are available in this data sheet. So you should go and search this number, which is the part number for the OLED, and download two more data sheets from the website. So you'll get this data sheet from the website, which has more information about what each pin means. So these pins are exactly same as this: VDD, VSS, VCC, etc. It's same. So it's same as this. So more information are given there. Now what we are interested from this data sheet is the timing diagram for SPI communication. Okay, so and the rating, the values also. So if you come to this page, okay, so this page is basically describing what is the clock frequency, typical clock frequency for SPI communication supported by this OLED. Okay, and the value supported, the minimum clock period is 100 nanosecond. That means the maximum clock frequency at which SPI communication can happen is 10 megahertz. Now remember, the clock coming to zinc from the crystal is 100 megahertz. So you cannot directly use that clock as an SPI clock because the maximum frequency supported by OLED for SPI communication is only 10 megahertz. In addition to that, you can also see the setup time, hold time requirement for every signal between zinc and OLED, and we should respect all these timing parameters, otherwise things won't be working properly. Okay, so keep this in mind. Clock cycle 100 nanosecond minimum. Now this is the timing diagram for SPI, how data should be sent over SPI protocol. Now remember, SPI is a serial protocol. That means you are sending one bit at a time. Even if you have thousands of bytes of data, you can send only one bit at a time. And this is the timing diagram for that. So you can see CS, chip select, should be low while communication happens. But as far as Zedboard is concerned, chip select is permanently low, so you don't have to worry about it. It's always low. And this is the clock signal, and this is the order in which data should be sent. So you can see it is D7 first, followed by D6, D5, etc. That means when you are sending 1 byte of data, you should send the most significant bit first, followed by the second most significant, and the least significant bit should be sent as the last bit. Okay, that's the order you should follow. Now you should also notice the clock edges where the data is being sent. So you can see this is the falling edge of the serial clock, and what should happen? The master should place the data on the falling edge so that the slave can read the data on the rising edge. So as far as we are concerned, zinc is the master and OLED is the slave. So zinc should place the data on the falling edge and the OLED will read the data on the rising edge. And if you follow this timing sequence, the setup time, hold time requirement are automatically satisfied. You can see. So this is the rising edge. So this is the setup time available, which is half clock cycle, and our total clock period is 100 minimum nanosecond. that means this will be 50, and this is the whole time available, which is also 50, but the requirement is only 15 for setup time and 15 for hold time for most of the thing. Yeah, it's between 15 and 20, but you are giving 50 as both setup as well as hold, so it will always satisfy the requirement. Okay, so this is what we are going to do. We will give the clock and we will place the data on the falling edge, and OLED, he might be automatically sampling it on the rising edge, and you should always place the least significant bit first, followed by the most significant. Now, one challenge that you may face is, again, traditional SPI, your clock can be a free running clock. The clock can continuously run, and you are controlling the communication using the CS chip, because only if CS is low, the data communication happens. If CS is high, there is no communication. Even if there is a clock and there is something on the data, that won't be transmitted. But on our board, CS is permanently low. That means you cannot have a continuously running clock. The clock should be present only during communication. During other time, the clock should remain high. Okay, the clock should remain high. Otherwise, if the clock is freely running, the OLED will be continuously reading from the data line, and we don't know what data is going. That will affect the operation. So this is what we are going to do. Whenever we need data communication, we will have clock, and whenever we don't want to communicate, we won't have a clock. Instead, we will have a high signal on the clock pin. Fine, so today we are going to design only this SPI part, and the remainder circuit we will design after testing our SPI. Okay, so basically today we are going to design an SPI controller. So I'm starting it as a separate project, and once we design this SPI controller, we will integrate it with the remainder of the circuit which we will build, and finally we will have the complete OLED controller. Okay. Okay. Now let's try to write the input-output interface for the SPI controller. So remember, this SPI controller will be implemented in the zinc chip, and it will be connected to the pin of zinc, which will be later connected to the OLED. Okay, so as far as the controller is concerned, we of course have a clock. Now this is onboard zinc clock. Remember, this is coming at 100 megahertz. Okay, that frequency you cannot change. Now we have a reset signal as usual. Now suppose how the SPI controller is going to work. So what the SPI controller is supposed to do is, this SPI controller, this circuit, will be getting 1 byte of data from some other part of the circuit, maybe later from the processor. He will get 1 byte of data, and he has to transmit this 1 byte of data over the SPI interface serially. Okay, so he's getting 1 byte of data, which is 8 bits, and he has to transmit it serially. So this is more like a parallel in, serial out controller. He's getting data in parallel. So I'm calling it data in. He's getting a 8 bit of data, and he has to send 1 bit at a time, or SPI. So the signals to SPI are output. Let me call it SPI clock, and output SPI data. Whether they should be reg type, we will see later. These are the two signals going to SPI. There is no chip select because it's not coming to zinc, it's permanently grounded. Okay. Now we need few more additional signal. So as I said before, the data to be sent over SPI will be provided by some other circuit. Now how that circuit will tell my SPI controller that a new data has to be sent. So again, remember, these are physical wires. So this is some wire coming from some part of the circuit. So those wire will always have some value. Now how the circuit which wants to send data will tell the SPI controller that a new data is available for sending. Okay, so we need one additional signal for that indication. So I am calling it input load data, something like that. So signal indicates new data for transmission. Okay, so this is load data, or you can say this is like a data valid signal. This signal is basically telling there is a new data for transmitting. Now same way, your SPI controller should tell the other circuit that he has finished sending the data so that he can give the next data. Okay, so this is more like a handshaking between two circuits. So that circuit is telling you new data is available, send it. Once you finish sending, you should tell him, okay, I have done finishing it, give me new data. If that kind of handshaking is not available, the other circuit, he doesn't know whether you finish data sending, and maybe he will give you a new data before the previous one was completely sent out, which will create issues. Okay, so you need handshaking and done send or something. So signal indicates data has been sent over SPI interface. Later we will connect these signals with other part of the circuit, or maybe later we will connect the signal to the processor itself inside Zinc, so that the processor can directly send data through the SPI interface with software support. Okay, so basically these are the interfaces. Now first thing that I'm going to do is to try to generate this SPI clock. Now remember, this is 100 megahertz and this is maximum 10 megahertz max. So we will try to run the clock at 10 megahertz so that we get the best performance. Now how can you generate 10 megahertz clock from 100 megahertz? There are several ways of doing it. I am trying to do a very crude way of doing it. There are better ways, we will discuss later. So in this, what I am basically doing is I want to divide this clock frequency by 10 so that I get 10 megahertz. I need to do 100 megahertz by 10 so that I will get 10 megahertz. So basically I will use a counter, and the counter will be running using this clock signal, and when the counter value reaches 4, I will toggle this signal. Okay, so counter from 0, 1, 2, 3, 4, which will consume 5 clock cycles from here. I will toggle the signal. That means if it is 1, I will make it 0. Then again I count from 0, 1, 2, 3, 4. I will again toggle it. So if it were 0, it would become 1. So that will create some kind of square wave whose frequency is 1 by 10th of this one. Now that counter, it has to count till 4. So it has to be 3-bit. Let me simply call it counter. Maybe initialize it to 0 here itself. Now this is what I am going to do. Always at such clock begin if counter is not equal to 4, counter plus 1. If it is not 4, I will increment it. If it becomes 4, I will make it 0. And now in another always block, what I will do is if counter equal to 4, I will do SPI clock is not of SPI clock. So this is basically the toggling of SPI. Now this is inside always block, so it should be declared as register. Syntax error. Oh, sorry. I put here at SPI data. I put SPI. Okay, so it will be clearer when we do simulation. Now, one issue that you will face during simulation is I didn't give any initial value to SPI clock. So as far as simulator is concerned, when you start simulation, this value is unknown. So it will be X, and if you take a negation of X, it remains X unknown. So we have to give an initial value. You can either assign it here, or you can write an initial block, or you can add the reset signal here and initialize this to 0 or 1. Okay, so I'm going to use an initial block, initial, and I'll say SPI clock is 0 initially. Now on real hardware, even if you don't have this, it will work, because this signal will always have either 0 or 1, and based on that it will toggle. But in simulation, if you want to see the signal properly, this should be there. Okay, so let's go ahead and check whether it is working properly on simulation. Start. So this is the external clock, which is running at 10 nanosecond. We are not using reset anywhere here, so it doesn't matter assign any value to reset. What we are interested is this clock. Okay, so let's run, and here you can see, let me put the counter also to make sure you understand. Okay, so look here, the counter value is 0, then the counter goes to 1, 2, 3, 4, and back to 0. Okay, now this signal was 1 here, and we wrote if counter equal to 4, toggle that. So make sure you remember where the signal is becoming 4. So although you can see 4 here, this is happening after the clock edge. Okay, so counter will be seen as 4 by this always block, or by this if condition, which is basically a comparator inside your circuit only on this clock. So as far as this clock edge is concerned, the counter value is still 3. The counter value is 4 only here. That's why we compared with 4 instead of 5. Okay, so only if I write like this, I have 1, 2, 3, 4, 5 clock periods here and 5 clock periods here. So total 1 clock cycle here is same as 10 clock cycles here. That means this is 1 by 10th. So if it is 100 megahertz, this will be 10 megahertz. You can measure that also. So we have our marker here. You can place it at the beginning of this edge. You can right click here and choose markers. At marker, you will have one more marker. That marker you can move to the edge, next edge, and it will tell you what is the difference between second marker and first marker. So it's showing like, sorry, first marker and second marker. So he's showing like minus 100 nanosecond, 45 minus 145 nanosecond. So the period is 100 nanosecond, which is the requirement from the data sheet. Okay, clock should be 100 nanosecond. So that part is done. You can close the simulation from here. Now later we'll have to slightly modify it, because as I mentioned before, if you use this code directly, your SPI clock is a continuously running clock. It never stops. And CS signal is always low. That means there will be always data going from Zinc to OLED, and we don't know where data is going. So we need to enable this clock only when communication happens. Other time this clock should remain 1. Okay, so we'll have to modify it later accordingly. So most probably this initial condition also I will change to 1. Okay, let's see. Now we will write the communication part. So basically this is a requirement. So I will have this data coming from somewhere, and I need to send it 1 bit at a time, starting from MS bit. Now to do this, you will need a state machine. Okay, because this cannot be represented as a single condition. What I should do on this clock will depend upon what I was doing before. So initially I will have to take the data, then I have to send 1 bit at a time, then I have to check whether I send all the data, then I have to say I have done sending. Okay, so there are multiple states, so you will have to write it as a state machine, and there is a standard way of writing state machine in Verilog, so we will exactly follow it. So okay, now we were always writing post edge clock, but this time I will go ahead and change it to neck edge clock, because as we discussed before from the timing diagram, the data should be sent during negative edge of the clock so that OLED can read it on the positive edge of the clock. Okay, so that's why I'm writing neck edge. Next, data transmission is happening using SPI clock, not using the 100 MHz clock. So this clock I will change to SPI clock. Begin end. So you should always have reset condition for state machine, because you need to initialize the state and all. So I will say initially I am in idle state. We will declare all these things later once we finish state machine. So initially I am in idle state, or whenever a reset comes I will go back to idle state. Okay, now suppose we are in idle state. So this is standard way of writing state machine, and you have to follow this style. So this is the name of the state, and here you will write what would happen if you are in that particular state. So assume you are in idle state, and your state machine will remain in idle state as long as you don't have any data to send. Now when you have a data to send, which is indicated by this signal, load data. Okay, so if load data okay, what should happen? If there is load data, that means you have some valid data here. So what we'll do is I will take this input data and store it in a register. Let me call it a cache shift register. It will be clear to you why it is called a shift register. we will use it as a shift register. So whenever there is a data load, I will take this data and I will put it here, and I will change my state to send state or something. Okay, so let's come to send state. Here I will start sending data, and remember how data should be sent. It should be sent by starting the most significant bit. So I already have my data here, shift reg. So I'm going to send its 7th bit, ms bit, as the output, which is SPI data. So again, we are going to use it inside always block, declare it as reg type. So shift reg 7 is SPI data. I place the first data here. Then I will shift register. My shift register left by 1 position, so that on the next negative edge, the 6th bit here will become the 7th bit. Okay, so I will write as 6 down to 0, and one degree 0 here. That means the 6th bit comes as 7th, 5th bit as 6th, 0th bit as 1st, so on and so forth, and I'm saying my rightmost bit becomes 0. Now remember, everything you write inside one state happens on the same clock edge. Okay, so on this negative clock edge, the 7th bit get transmitted to SPI data, which is a reg. Essentially, this is a flip-flop. So the 7th bit goes as the output of a flip-flop. Then the entire shift register left shift by 1 position, so that the 6th bit comes as 7th bit. And when I transmit data on the next clock edge, this 6 will be going here effectively. Now, how long you will remain in this state? You will remain in this state as long as you send all 8 bits of data. So there should be some way of checking whether I finish sending all 8 bits. Now to do that, we need again a counter. So maybe we need to count till 8, or we can do it 7. Let's see. So I'm making a 3-bit counter, so it should be also initialized. I'm initializing it inside reset. I'm also initializing it inside idle state. So before coming to send state, I'm resetting this guy to 0. Here what I'm doing is, if data count not equal to 7, that's the maximum value, it's a 3-bit counter. If it is not 7, I will increment it. Okay, and else, that means when it becomes 7, okay, that means I have sent 7 data or all 8 data. I will go to the next step. That means I have finished sending data. It will be clearer when we do simulation. I will show you. So I'm changing the state to something called maybe done state. So here I am in done state, begin end, and in done state I will make this signal high. So let's declare that also as reg type, to indicate that I have finished data sending. So this should be also initialized when you press reset. Okay. Now this information will be seen by the circuit who actually wants to send data. Okay, and when he sees the data, he will understand, okay, I have finished data. Now, how will you know that he has seen this signal? Okay, so again, we define it in this way. Whoever wants to send data, he will make this signal high to indicate he wants to send data, and he will keep the signal high until he sees done signal. And once he sees done signal is high, he will make this signal low to indicate like he has seen the done signal. So what I will do is I will wait in this state. I will wait in this state until the load signal becomes 0. Once I see load signal is 0, we can end. I will make the done signal low, because this signal low indicates that the guy who wants to transmit, he already saw this signal is high. So I'll make it 0, and I will change my state to idle. That's it. That's all your state machine. So you are in idle state. You are waiting for the signal to come. If the signal comes, you latches the data. You go to the next state. You also initialize the data counter. In this state, you are shifting the 7th bit, or you are connecting the 7th bit to the SPI data. You are shifting the register left by 1 bit, and if counter is not 7, you are incrementing it by 1 until it becomes 7. Okay. Now, once you have sent all data, you are coming to done state. You make the signal high to indicate you have finished sending data. Wait until whoever wants to send data to deassert the signal, load data. Once you see the signal is low, you deassert the done signal, go back to idle state. Now you have to declare all these things. That's why we have error here. So state, we have 1, 2, 3 state. So state is a reg to have 0, 1, 2. So you need 2-bit state. Now all the state variables should be declared as local params. Local param idle equal to t0. So wherever there is local idle will be replaced by constant 0. And we have send degree 1. Send will be replaced by 1, and done is equal to degree 2. Okay, so local param is a way of declaring constants in Verilog. Okay, one mistake is we didn't write case statement, case state. So that should be there. And here we need end case, end case. Our case, end case item. So let's shift everything by 1 position. Better to keep indentation, but you understand. Okay, so that completes the state machine. So let's simulate and see how much it is working. So simulation, behavioral simulation. Let's restart. False clock 0, 1. Okay, reset. False constant 1. Initially data in, let's keep it 0, and load data, let's keep it 0. And run. Okay, this is the signal. SPI data is read initially because it's not initialized. Ideally, we should initialize it to 0. On the reset, we will add it. Okay. Okay, SPI clock is running. Counter is running, which we have seen before. Now let's try to send a real data. So before that, let me remove the reset signal. Okay, now let me try to send a data. Okay, so force constant, I'm trying to send A5, which is 10100101 in binary. So data I give. Let me make the load data signal high. So this is the protocol. So practically this will be given by some other circuit which we will build later. Okay, so you can see Fi came, that got latched here on this negative edge of this clock. So remember, state machine is running on this clock. Let's see what happens. Let's put 1000 nans here and run. Okay. So you can see the SPI data, how it is going. So on negative edge it placed. Okay, and this will be seen by OLED on this edge. So this is 1 0 1 0 0 1 0 1. Okay, this is exactly what we wanted to send. And once it is sent, you can see the done signal became high and your state is stuck at 2, which is basically done state, and you'll be stuck at done state until this load data signal becomes low. So load data, let me make it 0, and you are out of the state. You will come back to 0, which is ideal state. Okay, so everything looks fine except, as I mentioned before, the SPI clock. See, the SPI clock is continuously running, so the OLED is continuously reading from SPI data. So after this point, you are not sending valid data, but still he will be seeing a data called 1 on SPI data pin. That we have to avoid. So basically, your external SPI clock should be running starting from here all the way to 1 2 3 4 5 6 7 8. Okay, it should run only till here. On this edge onwards, it should be flat, it should remain high. Same way, before this edge, it should remain flat. So that's what we need to do. Okay, so how can we do it? So that's where you can use the concept of gated clock. Okay, this SPI clock, we don't want it to continuously run. We want to run it only when data transmission happen. Now if you directly control this SPI clock, you will run into another problem because your state machine is running using the same clock. Okay, so if I say when the system begins there is no SPI clock, that basically means your state machine won't run. Okay, so what you need to do is you need a 10 megahertz clock internally generated, and your state machine should run using that clock. Then that clock should be gated, controlled, and given to the SPI clock. So this clock that I am generating here, I am going to rename it. I'm just calling it clock 100 to indicate, or clock 10 maybe, to indicate it's a 10 megahertz clock. And I'm changing all these things to clock 10. Okay, all of them became clock 10, so I need to declare it reg clock 10. Now this SPI clock, let's write like this, assign SPI clock equal to clock 10, okay, with some control signal. So if that control signal is there, SPI clock will be clock 10. If that control signal is not there, SPI clock should be high. It should be constant high. So again, you can do it in a different way. Effectively, this is a multiplexer. So I can write like, if clock enable equal to 1, this one. If there is no clock enable, SPI clock remains 1. Now I am using it with assign statement, so we need to remove it. Now from where we will get this clock enable, that also we need to generate, okay, from the state machine. So initially when the system starts, when there is reset, we will say clock enable is 0. There is no clock enable. When you are in idle state, then also there is no clock enable. Clock enable will be made high when you start data transmission. So here I will make clock enable equal to 1. Okay, and once you have done with data transmission, I will make clock enable 0. So clock enable is high only during this state. And let's come back and look at the wave diagram. If you haven't closed the simulation tab, instead of again running simulation from here, you can just click on this button, relaunch. That means he will recompile your code and simulation will start again. Okay, but that new signal is not automatically added to the wave window, so we need to add it from here. So now I have clock enable also. So let's restart and clock, first clock 0, 1, 10, reset constant 1, data in constant 0, load data constant 0. Now let's run for say 100 nanosecond. Okay, so we have applied reset signal. SPI data also we should ideally initialize it, so let me do it here. SPI data, let me make it tick P0, 1 tick P1, doesn't matter actually. Okay, now let me remove the reset, force constant 0, again 100. Now I remove the reset. Now let me load some data. Okay, force constant we'll use the same as before, A5, and load data signal 1, and let's run it. Let's see what happens. Now notice that SPI clock is flat now because your CE is 0 now. And let's see. Okay, now look at this point. CE became 1 because your state has changed to 0 to 1. Okay, that's when CE became 1. And let's see what data is going out. So here it is 1. So 1, 0, 1. One, 0, 1, 0, 0, 1, 0, 1. That's it. After that, the clock becomes flat again. So the only information seen by OLED is this much, because that's the only time where clock is available. All other time, clock is constant high. Okay, so done signal goes high. Now if you make load data force constant 0, done signal goes low. Now if you want to send another data, let's say F0, and again make node data high, and you can see it gets transmitted here 11110000. That is F0, and again run signal become high. Okay, so this is the basic design for SPI controller. I am not implementing it and running on the board because you haven't completed the circuit. We only have the SPI controller, and whether it is really working or not, you cannot see it directly on the board because you cannot connect these output signals to LEDs because they are running so fast. Even 10 megahertz is too fast for you to visually see whether it is working or not. So at this point of time, I'm just verifying through simulation. I'm satisfied, okay, it is working through simulation. And actually there is a way to test it on hardware, the SPI controller alone or any subunit of your hardware. That technique we will discuss in the next video.